Hi, welcome to another lecture on Calculus 3. Today we are going to start talking about double integrals and calculation of volume. So the topic that I have for you today is a review of a definite integral from Calculus 1. Then the main topic is just calculation of volumes, an approximation technique called midpoint rule. You might have seen this thing in Cal 1 or Cal 2. A definition of iterated integrals, Fubini's theorem, and how to calculate average value of a function of two variables. So let's go to the main topic today. Main topic is how do you calculate the volume. By that we mean that we have a certain surface in the three-dimensional space, z equal to f of x and y. Surface is above the xy plane and is sitting on top of a certain rectangle. We want to find the volume that is underneath the surface and above the rectangle. Right now we are going to assume that the function is positive for the region we are interested in, and then we calculate the volume underneath it. This is very similar to calculation of area under curves. Similar techniques are being used, similar notations are going to be used, and we are going to explain that by drawing parallel to the what we did in Calculus 1 and then going further. So today is kind of a very general introduction. First, we have a notation. So the notation that we have is so-called double integral. So for double integral, we are going to have the notation is going to be, well, actually a double integral, indicating that we are calculating a volume. We indicate the region over which we are calculating. R for us, right? R is the rectangle that we have down here. Later on, R will be a general region. So right now we have a rectangle. Our rectangle is indicated by starting x and ending x, A to B, and starting y and ending y from C to D. So our rectangle is going to be the rectangle. The way we write it is a range of values in the x direction. Then we write the multiplication sign, range of values in the y direction. So that is going to be a rectangle. The surface that acts as the roof of this on top of this region is f of x and y, and this acts as height, and area of the base is going to be area of the base is going to be shown as dA. We are going to try to explain what is meant by this notation here, and let's go ahead and take a look at what we did in Calculus 1. What did we do in Calculus 1? We had perhaps a function, let's say some function y is equal to f of x, and then we wanted to calculate the area from some starting location to some ending location. This was the interval over which we were calculating, so it was integral of f of x, integral of f of x dx over the region I. So I could write I meant I'm integrating from A to B. Now this acted as the height, so we had certain height. We had these rectangles. Yeah, these rectangles had a certain width to them. So the width was itself was dx. So that is dx, that is the width. The height is indicated as f of x. That's the height of the function. When we multiply this height with this base, what we're calculating is the area of that little strip or the little rectangle. So that's the area of rectangle, of a rectangle. And this integration simply meant the command of adding up all the contributions. So if I have another rectangle here and another one, each of them can be approximated by one of these multiplications, and then we add them up, and that gives us the area. Then we had the fundamental theorem of calculus to make it easy for us to do this thing. We calculated the antiderivatives and so on and so forth. So here we are doing a similar tactic. We have this that's going to act as the height, and this is going to act as the base. Let's go ahead and take a look at a little demo here to help us digest what is involved here. So let me get out of this and go to our calculus 1. In calculus 1 we had some curve given by some function f of x. So here's an example of such a function. And then we construct these rectangles underneath it. Area of each rectangle is calculated as the height times the width. The height is f, width is dx, and then the integration means summation of all these contributions. So if you had a function that was partially below the x-axis, that below x-axis would have counted as negative, and if you are all positive, that's just as well. Now what we are doing is going into one more dimension. Now we have a surface. The surface is above a region on xy plane. We take this region to be a rectangle to make it easy. So now we have a surface given by this f of x and y. Underneath this surface we construct these thin boxes. So each box has a base, is a small base. That's what dA means, element of area. dA refers to base area of each rectangle. F is the height. When I multiply base with height, I am calculating the volume. So we are calculating the volumes of each of these extra thin boxes. And double integral means we are doing a summation that is goes in both x direction and y direction. So you have to think about a much longer list of things to be added up than what you had in calculus 1. So that's what is involved here. So what we have here is the volume. So volume is equal to this. So again, how are we going to carry this out? Well, we have to create those thin boxes, and for doing that we have to divide our rectangles in so many strips. Right now we take all these strips to be of the same size to keep things simple, and then we are of course dividing x direction and the y direction. So if I go on the y-axis here and look at my strips here, that strip starts from certain y to certain next value of y, and the distance between these two is going to be our delta y. In same sense, when we are subdividing our rectangle, we have a delta x. Delta x is the distance between horizontal lines that are perpendicular to the x-axis. So this dA is going to represent that delta x times delta y. And then f itself has to be calculated from some point. So we aim for one of these boxes, for example this one. Then area of that element, that's going to be counted as dA. The height of the function on top of that, so we have to figure out what the height is going to be. So we go from here all the way up to the surface itself. That's going to give us our f of x and y. Well, of course, inside that little cell down here, inside this cell, we have many choices. So for now, we just pick some point at random. Later on, we are going to improve that. Instead of choosing randomly, we choose it with a certain level of wisdom to get some better accuracy out of our calculation. So the job is very straightforward, even though somewhat tedious. So what are we going to do? So if we are faced with such a calculation, first of all, we have to go ahead and take our rectangle and divide it up. So here is our rectangle from A to B and then from C to D. So we are going to start x0, x1, x2 all the way to perhaps xn, and then y0, y1, y2 all the way perhaps to ym. We are subdividing this to so many rectangles. On each rectangle, we pick some random point. So the rectangle itself has to be designated. So if I am on interval I here and interval j here, I'm going to label that rectangle as a rectangle ij. So ij, I comma j, refers to each of these rectangles. Of course, we have lots of them, but it's straightforward to think about what is involved here. Then we are going to pick a point here. So this point has a x coordinate and y coordinate, and you see in your textbook it's being labeled as x stars. Kind of hard to see here. So it's when they want to indicate that they're picking something in an interval, that is a common notation. X bar ij refers to the point that you have chosen, randomly chosen from that ij cell. So this is on the axis, this is number I. On the y axis, this is number j. And that cell itself is rij. So then you pick a point in that. That point has an x coordinate, has a y coordinate. Y coordinate would be y star ij. So just think about it as a point chosen from that particular region. And then what? Once you have picked your point, let's say if this you have chosen this point, from that point you go straight up until you hit the surface, and that height is going to be f of that point. So that's going to be the height that you have. So you take the height multiplied by the area of the base. That's the volume of this little box, or the thin box. Let's go back and look at what we meant here. So you have a long list of these boxes. Area of the base is area of each of those cells we had in the other window. And then f tells you what the height is supposed to be. You pick the f, multiply by the area of the base, then you add up all this long list of things, and then what you get out of that is your actual approximation for the double integral. Why approximation? Well, if you choose these rectangles big, and then of course you're going to have that so-called pixelation effect. You're going to have a very rough approximation. If you make your rectangles smaller and smaller, you get a better and better answer. And for a continuous function, this, as in calculus 1, it's going to, in the limit that your number of cells goes to infinity, your approximation comes out to be close to the actual quantity. So in practice, how you calculate this thing, or at least for the definition of it, you are going to have a double sum. Double sum indicates that we have to go in both x and y direction, and add up all the pieces. And then we have f calculated at each of those points we chose. We had a cumbersome notation for it, but let's just put it here. It's just good to know that this point is chosen inside the cell number ij, and then your element of area was delta x times delta y, and since we took all of these things to be of the this delta x, delta y were uniformly chosen, so we don't need to put any indexes under them. All delta x's are the same, all delta y's are the same, just to keep the work simple. Well, once we do all this entire summation, what we have is the volume. But of course, it's an approximation to volume. Approximation because these are finite quantities. If you let them go towards zero, your approximation gets better and better, and eventually you are going to have exact value. So our exact value is limit of everything I wrote up here. That is this double sum that you had. F, let me just abbreviate it. Limit of this as the number of cells goes to infinity. So that means your delta x goes to 0 and your delta y goes to 0. Sum of that is your is the volume you are trying to calculate. Okay, so in practice, that's how you do it. So if they gave you data, what you do, perhaps a map is given to you, the value of the function at each of these points given to you by a set of numbers. All that you do is to add up your numbers and multiply by the area of the base. As simple as that. Even though the notation looks rather scary and complicated, the process itself is very straightforward. Okay, what we need to do next. Okay, what we need to do next is to have a strategy for following so that things are not being done in a hectic, willy-nilly fashion. Some standards to be kept. Issue number one is issue number one is how do you choose these points? We said in general you can have them random, but then that creates another kind of a complication to deal with. So what we agree on is choosing all of these points in a specific way. For example, you can use the lower left, lower right, upper left. Better than all of these things is to choose your points right smack at the middle of each point. So we might pick these points at the centers. So when I pick my data at the center of each rectangle, I say I'm creating the midpoint rule. So if this is the center of the cell or center of the rectangle that we have, what we get out of our calculation is called midpoint rule. So midpoint rule has a good behavior in the sense that it averages variations out, and we get a much better accuracy this way than like choosing a corner point or choosing a random point. So let me remind you that that's one of the favorite things that we did in Calculus 1. So in Calculus 1 we said if you want to calculate these areas, take the height of a rectangle from the midpoint of your base. So we are picking this midpoint, go straight up, and then creating a rectangle here. You see the advantage is that this undershoot and this overshoot they kind of cancel each other out, and then you get a balanced picture. You look at here again, we are missing this little white region. Here we are gaining this little green one, and they are almost going to offset each other, and as a result we are going to get much better accuracy by using midpoint. Doesn't have any complication and many benefits. So that tells us when we want to choose the height of these boxes, we choose the height from the midpoint of the cell that is at the base of this thing. That helps us keeping errors to a minimum amount. So that's the issue of the using the midpoint. However you decide on the midpoint, next up the question that you have to answer for yourself is how do you add all of these pieces. Okay, remember you have to take all these rectangles and calculate the volume on top of each of them and add them up. That's a kind of a chore, but then however you want to do it, you have to have a systematic approach to it as opposed to just doing it willy-nilly. The situation is somewhat like the chores that you do, such as mowing a lawn, vacuuming a room, raking leaves, and such. You come up with a strategy. What in your mind you do that, even though you don't spell it out. So, for example, when it comes to raking, perhaps let's say this is a wall of the building. You take all these leaves and rake them to here, and then go back, perhaps rake these things to this location. When you're raking, it means you are adding up all those leaves. So you are on each of these rows, you create a so-called subtotal of all the leaves in that row. And then you do that for each of these rows. And once you are finished with this process, what is the final thing you do? Well, the final thing to do is to calculate sum of all these leaves. Okay, so what did you have? You had a pile here, another pile here, another pile, another pile. These are all subtotals. And then you say, okay, let's collect all of these leaves. You collect all of them, and perhaps all of that stuff can be collected in that corner of the yard. That's one strategy you can have. Of course, there's another strategy. You could collect all these leaves. In our language, it means adding up the volume of each of these little pieces, each of these boxes, and bring them all the way to this. And then you do the same thing here, raking all these leaves, which means adding up all the volume contributions of each of these little boxes. And then you add this one and 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 this one. You have subtotals now accumulated on this edge. And then you finally add them all up at this location. Of course, however you rake your leaves, you have the same number of leaves. It doesn't matter in which manner you employ this raking strategies. At the end, you have the same size pile of leaves. And believe it or not, that is the essence of the so-called Fubini's theorem. Of course, the theorem is much more mathematical for much more sophisticated functions than what we are talking about. But the essence of it, the way it applies to us, is that however you're going to rake your leaves, you have the same amount of leaves. So how do we express that? Expressing this is by so-called partial integration. Partial integration is same idea as taking all the leaves in one row and collecting them in one spot, or all the leaves on one column and collecting it in one spot. That's what is meant by partial integration. So let's go ahead and take a look at the idea of partial integration. So when we take these boxes, so we have these boxes, each of them representing how many leaves were in certain area of our yard. When we add them all up, that is equivalent to a so-called partial integration. That's just exactly like the integration we had in calculus 1. We are going straight on a line and then calculating the contribution in that direction. And then once we have that, we go ahead and add up all the little collections that we had. Fubini's theorem is the statement that these two approaches will give us the same result. To explain that, let me go back to the top picture that we had. Let's assume, let me erase what we had. So we are calculating the volume of each boxes. So let me, maybe I use this picture I had here. In this picture, we see a little element of area dA. dA is delta x times delta y. And this F is the height of the surface. You multiply the F by that area and then you add them all up. Well, you make a decision how you are going to add them up. One way is to go, for example, in this direction. You're raking it in this direction. So you are going to add up this, let's see if I can draw this thing carefully. Each multiplication of this dA with the height gives you the volume of one of those thin boxes. When you add up all the contributions from each of these, it is equivalent to raking your yard in this direction and creating a subtotal. That subtotal is going to be called a partial integration. Why partial? Because now you have to do this thing all over again. You have to consider another slice of your yard. Draw this one. So it's going to be this one. We have to overlap it with the previous one. We are going to go another sweep and put all of these things in this location. And then a third one. Let's see other colors we have here. Another color perhaps for this one, another color for this one, another one here. So that gives rise to the idea of iterated integrals. The idea of iterated integral is that you sweep in a certain direction and then you sweep in perpendicular to that direction. So suppose I want to, let me go erase everything we have so that it becomes easy to see. Suppose I decide to sweep in this direction. What does that mean? It means take the integral of f of x and y. That's the height. The height, I'm going to multiply it by the element of dy. Each of these steps that I'm taking, I am walking in the direction of the y. So I multiply by dy because I'm walking in the y direction. And I'm starting from c to d, so I'm going to write c to d. So this is a partial integral. Partial integral. For that partial integration, x is going to be considered fixed. So this x indicates the x at which you're doing this sweep. The sweeps, let's say, it's all happening in a certain x. That's the x you're holding fixed. Then what? Then the x can start from A and go to B. So x is going to start changing. Once this partial integral is done, we are going to have an integral that goes from A to B that is uh, physically equivalent to sweeping all the leaves you had collected here. The movement now is in the x direction. The movement is in the x direction. So we have one integral, sometimes referred to as the interior integral. This is the interior integral. And then we do the exterior. In this one is going to be the exterior integral. Okay, we said all of this depends on your choice of first direction versus the second direction. And Fubini's theorem is a general statement that however you do this thing, it'll be the same. Of course, for continuous function, this is almost obvious, but for more general function that Fubini was looking at, it was a tricky issue. So let's go ahead and write Fubini's theorem. Fubini, probably he raked lots of lawns, so he came up with the idea that if I have this function f of x and y, and then I go first in the y direction from C to D, and then I go in the x direction from A to B, and then so dx comes outside, what I get is the same that as I would have gotten if I had walked in the x direction first, f of x and y. Now I integrate in x. After this is all done, all of those sweeps are done, then I go in, collect all of those subtotals. I walk in y direction. So Fubini's theorem, let's just say for continuous f. For continuous f, this is true, and his statement was a lot more general for lots of other functions. That's still true. Okay, so hopefully by now you have a sense of what is it that we are doing, the meaning of it, and what is left is to do a couple of exercises to make sure we understood the steps that are involved. For the first exercise, let me start with something simple. So suppose I have f of x and y to be, let's see, just x squared y. And my rectangle is first, let's say, 1 to 2, and then say 3 by 4. We want to show by an example that Fubini's theorem is correct and actually calculate the volume. So we want to find the volume of surface that is given by this equation on top of this rectangle. So let's go ahead and write it. If I write C to D first, it's going to go from 3 to 4. X to y, so remember this is y direction, this is x direction. So y direction, I go there first, and x direction from 1 to 2 dx. Usually they don't put parentheses because it's messy enough without having any parentheses. But we have to keep it straight in our mind that there's actually parentheses there. So we go inside and do this thing. 1 to 2, x to y, has a simple integrals x to y2 over 2. Is that right? My y is going from 3 to 4. And then after that kicks in, what we have is dx. So we go ahead and figure out what this thing is from 1 to 2. x squared over 2. Remember, x squared over 2. This is, excuse me, this, sorry, this x squared over 2 is a fixture uh, in the first integration. It's the first integral with respect to y, so y became y squared over 2. X squared stays as it is, waiting for its turn for the next round. So x squared over 2 stays. Y squared is going from 3 to 4, so I have to take 4 and square it. I get 16. 3 squared, I get 9, and then I have to subtract them. So I write 16 minus 9, and then dx. Of course, 16 minus 9 is 7, and a 2 is a constant number. I pull that out. X squared dx from 1 to 2. So it's going to be 7/2 of, this is x cubed over 3 from 1 to 2. And that's going to be 7/2 of, now we are going to have 2 cubed minus 1 cubed, and then divided by 3. By accident, I get another 7. That is a lucky coincidence. 7 times 7, 49, 6. Okay. What if we wanted to do the same thing in the opposite order? That is, we go from 3 to 4. On the y direction, I want to do it at the end. In the x direction, I want to do it at the beginning. So it says x squared y. I do dx first. Once this is done, I'm supposed to do dy. Well, what we get here, sorry, wherever you touch, something happens. So we leave the y to wait, and then you have antiderivative of x squared is x cubed over 3 times y now, from 1 to 2, and then dy. That is, of course, from 3 to 4 of x cubed over 3. That's going to be between 2 and 1, just as before. It's going to be 7/3 times y dy. And then I integrate y, 7/3 y squared over 2 from 3 to 4. Just as before, I'll have 3 squared subtracted from 4 squared. That's going to be 7 times 7/3. I will get my result for 49.6. As you might notice, if my function f is such that x's are all separated from the y, like you see here, if these two x portion and y portion are separate and multiplied by each other, then all you need to do is to calculate the two integrals that you have separately and just multiply them out after you're all done. So what does that mean? Let me write it here. So if I have f of x and y to be some g of x times h of y, if x is separate the y from y's, and then I want to go from a to b of a to b of integral of c to d of f, now dy first and then dx last. I can do g, a to b of g, put all the x's separately, put all the y's separately. So if I was lucky enough that f was separated to product of x's and y's, this could have been done. But of course, more often than not, we don't get to be that lucky. Let's see. As a list of topics that we had for today. So we talked about similarity between what we do now and what we did in Calculus 1. We made sense of what the volume is supposed to be. We said in doing that calculation, midpoint is the easiest one to use and is the best in terms of accuracy. Among the simple rules, that's the best. Iterated integrals, simply the concept of going in the x direction and the y direction, raking one in one direction and raking in another direction. For the last item today, we are going to talk about average value. The idea of average value is the following. Suppose we have this surface here. Suppose this surface is like a surface of sand, and this is an actual box. Now suppose we desire to level off this sand. You know, sometimes you play with sand, you want to level it off. The question is, what would be the height of sand after you level it off? So this entire chamber or container, imagine you have like some glass chamber, and inside of that somebody has made this surface with the sand that you have, and you level it off. The question is, what is the height of that leveled surface there? Very simple idea. After you level the sand, the volume of it has to be same as what it was before. Let's assume your sand is not compressible, you're not tamping it down, pressing it down or something. You're just making it level. So if you're making it level, the volume has to be the same. If the volume is the same, then the height of your leveled surface has to be volume that you have already calculated divided by the area of the base. Okay, so average value of, let's go ahead and so we have the average of f over rectangle r is equal to, calculate the double integral of f dA over the rectangle r divided by area of r. Actually, true for any shape r, doesn't have to be a rectangle, but well, we started with the rectangles first, so that's what we are emphasizing. So let's give several other interpretation of this thing. Suppose F is amount of rain in different spots in a city, and you want to figure out what's the average rain in a city. So if you calculate somehow the total volume of all the rain droplets that fell, that would be this. Total amount of rain that came down would be this. If you divide it by area of the region on which that rain fell, well, you get the average rain, and the average rain is same as the concept of average that we are having here. It could be F is indicating of the depth of a lake, and you want to find the average depth of the lake is going to be the same concept. So in your exercises, you're going to see many other applications of this concept. If you want to find out the average of something, you just do an integral, and then you divide by the size of the base that you have. You have to again make some assumptions at the outset before you go on. Typically, a picture that is given to you, like some particular shape or item, typically what you have is some sort of a contour map. Contour map of something. This looks like a physics application, but in practice it could be contour map of the rainfall, height of a mountain and something, and say you want to calculate average of a certain quantity over that region. Well, this contour map is supposed to be understood in the following way, that in this neighborhood, whatever you're calculating is almost 30. And here, say this is amount of rain. This is like perhaps 20 inches of rain here in some hurricane, and then there was 10 inches of rain around this neighborhood, and so on. You want to figure out what's the average rain. First of all, you have to decide how accurate you want to be. Uh, High accuracy means you have to do a lot of calculations over a lot of pixels. Low accuracy, well, you want to be quick calculation, you want to be done, and you want to go. So let's say we want to be quick at the end of this lecture. What do? We agree that we take this thing and subdivide it to a few rectangles. Well, here is as rough as I can make it. So I have 4 rectangles. Okay, 4 rectangles. Now on each of here is one rectangle. Here is let's say here is another rectangle. Here is let's see, does this work? Here's another rectangle, and say here's another one. On each of these things you have to choose a point. We said the best approach is choose the midpoint. So we are midpoint here. So here are midpoints. At these points we have to pick a representative value for each of these squares that we have. So what do you think is a good idea here? I am between 10 and 20. You have to kind of eyeball it to see what is it to be, what's a good value in the middle. It looks like 15 is good. Here I'm between 10 and 0, so here maybe 5 is good. Of course we can debate that and get more accurate, but we don't have that much time. Here we are between 20 and 30, so perhaps I allocate 25 here. Here I'm right smack on 10, so I just choose 10. So the total volume, we take area of one of these things. So right now this is 2. Let's see, this doesn't write here. 2. This is also 2. So the area of the base is 4. I take 4 and multiply by the height at each of these places, 15 and 5 and 25 and 10. We want it to be quick, so it's going to be rough. So what do I have? 20 and 10, 30 and 55. So it looks like 4 times 55. Let me double check. 20, 45, 55. Total volume of, say, rain here was 220. That's 220 gallons or whatever. The average is going to be this total value you calculated divided by area of entire region. Area of the entire region. So what's the area of the entire region? Area of the entire region is 4. This is 4 by 4 is 16. So I take 220 and divide it by 16, and let's see, what do we have? 220 divided by 16, get some number, almost 13.75. It kind of makes sense between all these numbers I had here. Lots of let me erase these things so you can see what was here to begin with. These are our original numbers. Makes sense. The average is at about 14 or something. So if it was amount of rain, it'll be 14 inches of rain in this region after some perhaps hurricane or something. So that is how we do averaging. So we are done with this one too. we learn how to calculate the average value. What you want to do is to read the text carefully one more time, familiarize yourself with all the technical terminology, get the sense of going in one direction and another direction. That's the most important concept here, because we are going to look at integrations where it's not simply on a rectangle. It's going to be some kind of a odd looking region and such, and detecting in which direction you are going and where you start and when you stop. Those are important things that are going to be crucial for us in the future. So, uh, so I guess we are done for today. We have covered the additional material for this chapter, and hopefully I'll see you again. Good luck and God bless until next time.